Let's get started. So we're happy to have Dongsheng Ge from Osaka University. He's going to tell us about interacting conformal line defect with theories. Can you take it away?
Thanks for the introduction, and thanks a lot for Ivan to arrange this seminar for me. So today I will talk about a work that we had put out in October with Chris Herzog and his student Sam Bartlett-Tisdall. Let me start with some introduction. So defects are very interesting objects in nature, and they have appeared in many different situations. But in our concern, we want to understand it in a more in a pure theoretical setup. And as far as I can tell, defects are possibly the simplest objects. That we can have, and they are also ubiquitous in our physical world or in the theoretical concerns. And some examples I can think of, for such as the Wilson-Hooft line. I mean, I can do those. Yeah, you know that. As well as impurities. In some condensed matter system, and we will have oscillate strings. And there are many other examples about line defect. So theoretically, especially, we can use analytical tools to analyze those line defect. This relies on a setup where the bulk is at its critical point, and if we can trigger an RG along this line defect, it can also flow to a conformal fixed point. And in this case, we have good control because the conformal group now actually breaks into the residue conformal group part and the transverse orthogonal group. Those are purely rotations in the transverse directions. The question we are trying to ask in this work is the following. We want to ask if we have a free bulk theory in the ambient space or in the bulk space, can we still have some non-trivial defect? Meaning that we have can we still have some non-trivial dynamics along the line? We can think of this non-trivial dynamics as if we can have some interacting theory locally along the line. And to answer this question, we mainly consider.
But of course, you can have interesting quantum mechanics that live on the line, which you will call dynamical. But here, I guess you want the quantum mechanics also to be coupled.
Yes.
To the bulk.
Yes.
Free degrees.
Exactly. Thanks for the clarification. And our main concern here is a free scalar field theory that so you might think such a simple model or simple setup must have been considered in the past. And indeed, they have been considered in the past. In fact, in 2020, there was a work by Laureate Liando, Van Rees, and Zhao, and they have studied a series of a few. They have made some categorization for the non-trivial defects in the general dimension, and they had a claim to this question that we cannot have an interesting or non-trivial line defect in the when the bulk theory is free, and they made
Apart from monogamy line.
even for monogamy lines, they think they have made a classification such that the only non-trivial defects are codimensional 2 monogamy defects for V larger or equal than 4 spacetime dimension.
Yes. So in 3-dimension, well, in 3-dimension, you have non-trivial monogamy line, which is codimension 2.
The categories to be 4.
No, but the 3-dimensional monogamy line is non-trivial.
Uh-huh.
So their classification is saying that first, what they call trivial is not what people usually mean is trivial. I'm not sure if that's going to be relevant for your talk. But second, even in their classification, the monogamy lines or monogamy defects in general, which are codimension 2, are not trivial according to their classification in any dimension. So that includes the line in 3-dimension. In 4-dimension, it will be a surface.
Right. Okay, maybe they have some assumptions. So in their assumption, if we have a reflection positive setup, then they were saying that the non-trivial, even monogamy defects can only exist for these larger than 4.
Monogamy line does exist in 3-dimension. It's just the Aharonov bone phase.
Yeah, I think that makes sense. Okay.
And it was ultimately studied both on the lattice and also in the continuum in this work from Bartlett-Tisdall and Komakowski and yeah, maybe another author. I forgot. Yeah.
Okay, that's good to know. Thanks for the comment.
But their notion of trivial defect is a little bit unconventional. So
yeah. Maybe I will explain.
maybe it's not relevant. Is their notion of triviality relevant for your talk?
Yeah, their notion is relevant.
Okay. So you will explain.
I will explain what does trivial in their sense. So as Ivan pointed out, there are actually some other types of theory which contains non-trivial monogamy defects, monogamy line defects, and in this talk I care more about the normal defect. And then in this work they have made the claim about the conformal line defects, and then they basically says that triviality. They claim that conformal line defects are always trivial in the sense that the bulk endpoint function are completely fixed. This is because of the following 2 reasons. The first reason is that they found out the defect correlations are of GFF type. And GFF means generalized free field. And the second observation is that when we consider bulk to defect OPEs, this OPE doesn't really involve any other field contents. So in a sense, the bulk field, when expanded towards the defect, it behaves like, so let's say Y is the orthogonal distance, and then you can always expand it schematically as as a field with transverse spin L. So those are all the sectors one can consider for the bulk-to-defect OB. And based on these two cases, then it's not hard to see once when you expand the bulk field towards the defect, and then the defect correlations are always somehow trivially. One can use weak contractions to do that. And in this sense, we can calculate all the bulk endpoint functions, and they are completely fixed. This is their triviality claim. And in order to get this claim, they have a few assumptions. So the first assumption is actually they assume the classical equation of motion is still valid for the correlations. When the bulk insertion is away from the defect, so when the transverse direction or the transverse distance is not zero. The second assumption they have made in this analysis is that the time reversal symmetry is actually preserved. And this assumption actually helped them to, when they analyze the bulk defect three-point function, and by assuming time reversal symmetry, they can kill some unphysical singularities in their conformal blocks, and that to remove the unphysical singularity, then they get a double twist condition. For their defect OPE. And the third assumption they have made is the following. They assume that the identity, the defect identity, when I use a head, this means the operator on the defect, is the only zero-dimension defect operator. As you can imagine, if that's the only defect dimension zero defect operator, then this ensures cluster decomposition. And this cluster decomposition is related to their GFF claim. And so in our understanding, we think we can still assume this assumption that if we use the equation of motion as an input constraint to get some useful information, but somehow we think the second assumption and the third assumption are not necessarily a good assumptions. It is because you see, for general quantum field theory, we usually require CPT invariance, but time can actually, the time reversal invariance can actually be broken. And we want to break this condition. And the third condition is that we can actually construct explicitly some dimension zero operator, defect operator other than identity. So our claim is that, well, we think that these two conditions can be broken explicitly. So I will make a general analysis about this one, like to provide a general analysis on the bulk defect three-point functions, on how this wouldn't be a problem. To break the time reversal symmetry wouldn't be a problem. And I will also construct an explicit example to show that indeed we can construct other dimension zero operator in a given model.
Just a comment, I think the assumptions they made are just simplifying, to simplify analysis, there's no principle that forbids from you to have time reversal symmetry on the defect. Just that because the bulk theory they consider free scalar theory has time reversal symmetry, so the starting point is considered defects, also respecting that symmetry. But as in any case, we have a space-time of global symmetry in the bulk. You know the defects are already breaking transverse translation symmetry. You can ask the defect to break more symmetry. So I mean, this is a natural option. And also to have multiple identity operators is also a very, very simple possibility because the moment you have a single defect, you can take direct sum. And when you take direct sum, you have degenerate identity operators, which are essentially the projection to the individual summon in this direct sum, describing this composite defect. Yeah. So there you can say that their claim is gonna be about the building blocks of this more general defect, assuming the blocks themselves satisfy time reversal symmetry. But yes, there will be more possibilities. Probably will tell us.
Right. Yeah, so now I'm heading to, thanks for the comment. Now I'm heading to our consideration how to violate those two assumptions. And we will still assume that the first one is still valid for the analysis. So my outline today is first I will
and also the first, would you say it's assumption? I guess it's not. If you assume the defect is local, then it would not really be an assumption, right? Because you expect the equation. I mean, the equation motion is going to be in this case should be thought as a word identity for the operator phi because it's a special representation. It's one of the protected representations because of free scalar. So this is just word identity associated with that correlator.
Yes.
If the defect is local, then this will be satisfied.
I would more think it's the Schwinger-Dyson equation.
You can also think about Schwinger-Dyson if you're thinking about in the path integral perspective. But in the operator language, it's because phi is a special operator. It's a special representation of a conformal group. The specialness of that representation is captured by this Laplacian, giving rise to the shortening condition.
So indeed, here we have neglected the counter terms when phi is closing to the defect. Okay, very nice. So first I will follow their procedure to consider a two-point function, which is the bulk-defect two-point function. And the equation of motion can actually fix the defect spectrum. And then I will talk about three-point function, which is the bulk-defect three-point function. And more specifically, I will construct a new cross ratio, which are very specific to the line defect actually. And this new cross ratio will break the inversion symmetry or the time reversal symmetry here. And in the third part, I will construct an explicit localized Yukawa interacting model with Yukawa interaction. That couples phi to the line.
Just a question, sorry if you already said this.
Yeah.
Does D have to be greater than 2, or can we consider?
That's a good point. So actually, the space-time dimension here, we consider it to be larger than 2. So indeed, their claim doesn't apply for two-dimensional case. Thanks. Right. So now I will start with.
Dimension has the other problem is if you consider the non-compact scalar.
Yeah.
Don't have a normal form.
Okay. Thanks a lot for the comments. So now let me consider first part. The first bulk to defect two-point function. Actually, let me use x mu as t and y. T is the direction along the line, and the y's are the transverse directions.
Is it true that throughout analysis you assume the defect is unitary?
I will use the spectrum to. I will put constraint on the spectrum.
Okay, so you
to get a unitary field.
Okay.
And the two-point function are actually fixed by conformal symmetry. So here I can consider an operator with arbitrary transverse spin along the line, and actually this notation has basically means that we can use null vectors to project this operator to be in the traceless symmetric representations. And this bulk defect two-point function is actually fixed to be up to a BOE coefficient. And the numerator part actually carries the transverse spin, and the denominator part is purely fixed by conformal symmetry, with delta L to be the conformal dimension for this defect operator. And by applying the equation of motion on x1, then this is 0. And this leads to the solution that the defect spectrum should have 2 branches. First branch is the delta plus the spin. So delta is the classical dimension for also the quantum dimension for this phi operator, including quantum corrections. And the other branch is actually 1 minus delta minus L. So these two solutions are actually shadow blocks of each other. And to answer Ifan's question on unitarity, so basically in these 4 dimensions, that will be our main concern in this work. And in this dimension, we know the scalar operator has dimension 1, and to have a unitary theory, somehow the first solution behaves well, but the second solution we can only take the spin 0 solution. So we will have the unitarity fix the defect spectrum to be in the following case. And now we can consider the bulk defect-defect.
So there you meant that the integral part, apart from the L equal to 0 mode, all the other ones you have to pick choice. But for the L equal to 0, you can pick 2 choices, either 1 or 0. That's what they meant, right?
Yes.
And one choice is going to be trivial, and the other choice is the one you wrote down.
Yeah. Okay. That we have to fill out the other non-unitary part.
No, but I just mean that there. So you only wrote one. You only wrote delta. You wrote delta 0 equal to 0 or delta 1 equal to 0.
Ah, sorry. Maybe. So this is the allowed spectrum. This is delta 0.
Right. So the delta 0 could be 1 or 0.
Okay. Let's put it delta.
Sorry, what does the box? How should I read the second equation?
Okay.
In the formula, what is L? Is
L. So this solution corresponds to the first solution.
Yeah. And
we also have a second branch. That can only be like.
I can only make that choice for L equal to 0.
Right. L equal to 0 is the only allowed solution for unitary theory. So
the conclusion is that I have 2 choices, right? I can only make a choice for L, and for that value, for L equal to 0, and for that value of L, I have two choices.
Right. When L equals to 0, we have two
Okay.
operators, let's say.
No, for L equal to 0, there are two choices or two operators.
Yeah, two choices. Maybe there are degeneracies on the operators. One has conformal dimension 0, and the other has conformal dimension
in principle, but you have to tell. Yeah, okay. At this level of looking at just this correlator, there are multiple operators. One with dimension 0 and one with dimension 1. That's what they meant. I mean, later on, you will talk about the OP coefficients.
Right.
Okay. Because the coefficient may not be both non-zero.
That's true. That's true. Right. Thanks for the comments. So now let's consider the bulk-defect-defect frequent function. And in this case, in their case, actually they okay, let me just do it. When we consider a bulk-defect-defect frequent function, we have actually three insertions now. And normally we can construct a cross ratio that's using the distances. And this in Lorentzian signature will actually gives us the following result. And for this cross ratio, actually, it is invariant under time reversal symmetry, as you can see from the time component plot. And let me tell you a bit more about this cross ratio. Actually, it would be easier to visualize it in Lorentzian Euclidean signature. So let me use Euclidean signature to tell a bit more about this cross ratio. And so this we have three insertion points, and we can use the conformal symmetries to fix those 3 points on. Let's say we put T2 at 1 and T3 at -1, and then we can also put the bulk operator on the real, not on the real, on this axis. So in their analysis, they have figured out once we do in this way, we can form a circle or sphere. We can have a sphere that is formed by the two defect operators at the North Pole and the South Pole. And what they have realized that if, first of all, the bulk operator now is mapped to the cross ratio, and when we fix it in such a way, we have the cross ratio to be like 1 plus 1 by 1 squared, the total squared, and then 4 by 1 squared. And you see very clearly that this cross ratio is inversion symmetric. So the inversion here actually maps y1 to 1 inversion. Maps y1 to 1 over y1. And this expression is symmetric under this transformation. And pictorially, this basically means that we are mapping the bulk operator outside the unit sphere to somewhere inside the unit sphere. And this will cause actually some ambiguity because we have one cross ratio, but it can correspond to two different locations of bulk operator. So it's a 2-to-1 map. That's the first comment. And the second comment is that in their analysis, when they find, so actually they find unphysical singularities, and this unphysical singularity is exactly when the bulk insertion is crossing this unit sphere. And on this unit sphere, they find the unphysical singularities. So in principle, we understand that there shouldn't be any singularity along this unit sphere. And that leads them to say, okay, we should have double twist conditions. And apparently, in this situation, not apparently, but actually in this situation, we can construct another cross ratio that is not symmetric under inversion, and it can distinguish whether a point of bulk insertion is outside the unit sphere or inside the unit sphere. And this cross ratio, we find out it to be more or less like we take square root of 1 minus this cross ratio, but we have to multiply it by a sine function between t to 3, t to 3. And the new cross ratio we have constructed is the following.
Where's the defect in this picture?
The defect in this case will be along the vertical direction.
So is inversion invariant?
Yeah.
Inversion by origin.
Yeah, that will be the defect line. Right, so let me use the Euclidean signature here to write down the expression for the cross ratio. So it will have the following form, and if we substitute the explicit value for T2 and T3, which we have fixed, and it will look like y1 squared minus 1 over T2 minus 1, 2 times y1, absolute value, the distance transfers to the defect.
With a higher dimensional defect, you always have two cross ratios. So if you let's continue that expression in dimension, you probably will end up with this pair, right?
In higher dimensions,
And the defect, if it's two-dimensional or more, you always have two cross ratios. Is it true that if you write it in a way that's, that makes sense to continue in dimension, you will end up with?
Yeah, that part I'm not entirely sure.
Because this kinematically, this will be the same as a 4-point function in the space where the dimension is the same as the defect dimension.
Both defect, I thought we only had one
for line defect. Just think about two dimensions. I mean, because by this doubling method, this 3-point function can be mapped to a 4-point function. Kinematically.
Yeah.
You have two independent cross ratios.
That's right.
If the dimension of defect is bigger than 1. Yeah. But I'm saying that this pair presumably can get. I mean, it's just like a sphere continuing to one dimension become like a S1 with 2 points. I think.
Right.
There's order between the 2 points that's going to give you the second cross ratio.
Right. So in a higher dimensional defect, the issue that so if we want to still construct some there are two different points. So first of all,
you have an angle. You're something like an angle.
Yeah,
there's an angle will become the order.
Yeah.
So here you have a size and an angle. Sorry, in higher dimension you have a size and an angle. The angle I'm saying that in this lower dimensional case will be the second term.
Yeah. That's right. And also in the higher dimension part, if we want still to construct something like this, probably we need to take absolute value.
Yeah.
And in that case, I'm not very sure whether it can go from like it is related to this one or not.
It's not related to that. You have two independent cross ratio in higher dimension. You can write in terms of one is like a size, and that's like your first cross ratio. The other is angle. I'm saying continue that angle cross ratio down to one dimension. You will find it will be this. I think it's going to be related to your second.
Yeah. I can imagine there are good ways to separate the angular dependent part and the side dependent part. What I want to say here is that this two actually is somehow related. This nu e and the zeta e is somehow related as a square root. So nu e, roughly speaking, is zeta e minus 1. So this simple relation somehow probably is very special in.
Yeah, it's because we have S1. I mean, the side the same, right?
Right. There couldn't be an angular dependence on this tau 1, 2, and tau 1, 3. Actually, there should be a sign of the inverse. And you see that this nu goes to 0 when the bulk insertion is hitting on the unit circle. And then you can also see that this new cross ratio is not symmetric under inversion, and actually it gains an extra sign under inversion.
How come people didn't consider this cross ratio when they study, SYK, when they study correlation functions of fermion? How come they did not consider this cross ratio? I mean, would this cross ratio also not play a role?
Have Y1.
You say this cross ratio is only non-trivial when you have a separate.
Yeah, you have some transverse distance.
Okay. Yeah, indeed, this is not one.
Right, and an extra comment is related to what Yukawa was saying. In higher dimension, such a simple way to relate the two cross ratio is not available, as we will have an extra angle between tau 1, 2 and tau 1, 3 in higher dimension. That's nice. So, and now we can actually express our conformal block in terms of this new cross ratio rather than the one that they have used. So the one they have used assumes it is time reversal symmetric, but in the one we have using, it's actually time reversal broken, and it breaks the time reversal symmetry too in a very interesting manner. Just get a minus sign. And now we can.
But maybe you could say that it's really the sign part that's important.
Yeah, here the sign part is important.
I mean that itself is an invariant cross ratio. And that of course is encountered in SYK, just coming from the fact that you're dealing with fermions as opposed to bosons.
Yeah.
If you study bosonic versus fermionic case, you will see this difference. Okay.
Yeah, this sounds like some kind of -1 to the f. Right, I think I have only 1 hour, right? So maybe I can speed some details of this 3-point function analysis. But so now the logic is that we can basically express the bulk-defect-defect 3-point function using this new cross ratio, and considering their spinning structures. Those spin are the transverse spin. We can actually have the following answers. So we have one normal vector from the bulk insertion, and then we have a null vector from the first defect operator, and we will also have a second null operator corresponding to the second defect operator. And then here we can write the expression in such a way that we take out all the null vector dependence and not dependence, but the degrees of freedom. Sorry, the degrees. And the denominator is fixed purely by the conformal. The kinetic part comes from, it is fixed by the conformal symmetry. And for the conformal block part, we can decompose it in such a way that it can be written into a product of two functions. The first function only depends on the new cross ratio, and the second function depends on a kind of new cross ratio, and this new cross ratio is related to the spin structure as I was saying that you see those on the left side and on the right side, they should have the same degree of spinning degrees freedom. And here we have P2 to the L plus L3. So here we have assumed that L2 is larger than L3, and P3 has only L3 part. So these two matches, and that means for what is inside this sum should have 0 degree of P2 or P3, and then we should divide it by P2 times P3. And similar to the bulk defect two-point functions, now we need to act the Laplacian on this three-point function, and that will give us some constraint on the conformal block part and the spinning block part. And those basically are second-order equation. So once we act this on the three-point function, we can decompose the equations into two separate equations. And the first equation, roughly speaking, will be some A of cross ratio. So both equations will be second-order differential equations. I just write it schematically, and as you can expect, that the part related to the conformal block should be an eigenfunction of the residue conformal group as SO1, 2, and it should have the eigenvalues that behaves like delta times delta minus 1. And the second equation, for the H part, it will behave similar. No, it will have a similar form. It's still a second-order equation. And it has eigenvalue, which is L times L plus D minus 3, such that these eigenvalues actually comes from the orthogonal rotational group. And then to solve these two equations, as we all know, if both of them will have two different branches, since they are second-order equations. And for the H part, we need to impose boundary condition such that when this cross ratio is 0, we goes back to the only kinetic part, and this will be roughly 1. Let me tell you a little bit more about equation 1. This is also one black.
Typically use the boards that can be moved around. That board is stuck.
I see.
So you won't be able to.
Maybe I just erase this part. So basically solving the equation 1, we will find solutions that f of u will be like mu minus 1 to the power del 2 plus del 3 over 2, and it has two branches that can be expressed in terms of a Legendre polynomial, and both functions, both Legendre polynomials, are actually regular when nu equals to 0, meaning when the bulk operator is around the blue sphere. So the solutions are actually regular when we write the conformal block in terms of the nu cross ratio. And this is to show that we didn't encounter this unphysical singularity, and then in this case we don't really get double twist condition as they did. And then the double twist condition is actually crucial for them to prove in a general sense that the conformal line defect is trivial. So that general claim in our case is not really there.
So can I ask, it's not totally obvious to me that there's regularity at this blue sphere because of the sign that you have in front of the square root. Is it, I mean, that function doesn't look regular when you cross the blue line naively, like it doesn't look at C infinity, at least. Is it? Am I missing something? Or is it that you're only taking two derivatives and so you don't care that it's smooth? Or what exactly is the?
So I think this, okay, there is no absolute value here when we write the cross ratio in terms of the insertion points.
Okay.
It's not absolute value here. It's the normal bracket.
And then the y1, there's an absolute value of y1?
Well, yeah, y1 is the transverse distance.
Yes.
That only depends on the.
But that's what varies when you cross, to go across the blue line, you vary y1.
But you can rotate in the other direction, go around like that. Y has three extra directions.
Yes.
Okay. Right, because we're in at least 3 dimensions.
Or
Right.
four dimension.
Right. But still, if you keep y so real or whatever, you don't change the angles, and you just move it across the blue line in this plane, and you take some derivatives with respect to y, don't you get a singularity?
You mean across the defect?
No, I mean across the because it's y equals 1 is the location of the
Yeah, y equals to 1 is
oh,
the
that's the
location.
location here. So, all right, so the problem potentially would be there, but you say it's regular there. Okay.
Right, and so the more clear way to see it, okay, that is already already good, and then we can actually analyze the behavior of the Legendre polynomials around nu equals to 0, and these solutions are actually regular around nu equals to 0.
Okay.
So in another way, we can say that we don't really have singularity around those spheres. And in that sense, we don't really need the double twist condition on the defect spectrum. So that double twist condition is actually quite crucial in their proof for the triviality. Okay, so this is what we can reach so far about a simple input with the equation of motion as a constraint. And since we cannot get a double twist condition, it's hard for us to get a general statement whether a line defect is trivial or not. However, since the system is still very simple, we can actually construct a simple model to show whether it is trivial or not. That's what we are doing for the next part. And this kind of model is actually very simple. It is a Yukawa interaction on the line that couples to the bulk field, and we can write the interaction on the line to be the following. It has a kinetic term of Fermi, and then plus the Yukawa interaction path. And we also add another term that Ivan likes, which is the finite type of defect. And actually, this gives a boundary condition for the bulk scalar field. And in this theory, it has two nice properties. And actually, basically, that explicitly breaks their two assumptions. So the first nice property is that this action is not time reversal symmetric. This is because under time reversal transformation, psi goes to psi bar, and psi bar goes to psi. And we should also take into account the anti-unitarity of the time reversal transformation. And in this way, you see that the Yukawa term, psi bar psi, with phi goes actually to psi bar. We assume that the scalar is actually a scalar, not a pseudo one. And this equals to 1 minus psi bar psi times phi. So this term explicitly breaks the time reversal symmetry. And secondly, it has a protected operator that is dimension 0. How can we see it? We can consider the full equation of motion for phi, and this gives us. We also include the contact term here. And by dimension analysis, we can see that box phi in deeps to 4 dimension. Phi has dimension 1, and the box gives us 2. And this cancels with the dimension of the delta function. So this operator this operator is basically a protected operator, and it has dimension 0. So there's another dimension 0 defect operator along the line. So basically, those two nice properties of this simple model violates their two assumptions there. However, the triviality actually still holds for this model because it can be completely solved via the following trick. The trick is there might be some interesting thing here, actually, because we can actually use a field transformation or redefinition to make this theory to be like a free theory along the line. And the field redefinition is the following. So basically, we can absorb this Yukawa term into the definition of into a redefinition of psi by taking the exponential of ig times this phi to some fermionic field, and similarly with psi bar. And then you see through this field redefinition, basically the action becomes just a kinetic term for the free firm. So in this sense, we can basically calculate all the possible correlation functions in this theory. So in this sense, it is still a trivial theory. However, why I'm saying, and why I put a quotation mark for this free here, is because actually when we consider the conformal dimension for the fermion, it is actually not zero. It got corrections from the Yukawa interaction. So it acquires anomalous dimension. And in this sense, it's it seems like a free theory, but it's actually not really free. And also we can consider
This is the exact.
this is exact.
Yeah.
This is exact. And this can be obtained by considering the correlation function. Right.
And H remains marginal.
H remains marginal.
It cannot be. Or is it still the case? What is the nominal dimension of phi? How does it depend on G?
Phi doesn't depend on G, the quantum dimension of
The anomalous dimension. Does phi develop anomalous dimension?
the bulk phi doesn't.
No, on the defect. The phi hat.
On the defect, I think no. There is no fixed point for H. H is exact marginal.
Without the coupling to the fermion, yes. With the coupling to the fermion, there could be additional singularities that will lead to the running of H.
Uh-huh. Yeah, I think based on my impression, it is still like the anomalous dimension of phi on the defect is not really corrected by H. Yeah, I would think about
And the anomalous dimension of psi does not depend on H.
doesn't depend on H. That's correct. Right, and maybe I can talk about the last thing that can be interesting in this model. Okay, there's one extra thing that you might wonder whether our model, the model we constructed here, if we calculate some 3-point function, the bulk defect-defect 3-point function, whether that will be predicted by this general analysis. Actually, it does. So that's probably some kind of application one. We use this model to consider a bulk defect-defect 3-point function. And actually, the form of this 3-point function looks like IG over 4 pi squared hyperbolic times inverse 1 over mu, and then the 3 G squared over 4 pi squared times y1, and we put tau 2 to be in the future of tau 3. And actually, this agrees with the general analysis. And so in this case, actually only L equals to 0 block contributes. And if in this case, actually we pick the branch that the spin 0 operator has dimension 1. And the secondly, actually corresponds to Q0 equals to Q0 in this case for the spin 0 operator. It is hyperbolic tangent inverse.
So what is the dimension equal to 1, L equal to 0 operator in terms of your explicit construction? Psi bar or something else?
Yeah, that's a good point. So we think it will be a mixture of the original bulk field on the defect and this field, because this one has dimension 0.
Psi bar has dimension 0.
Psi bar has dimension 0. So it might be a mixture of the composite operator and this operator.
But what about the other combination? What is the dimension of the other combination?
You mean delta 0 to 0?
Because this combination, as you consider the weak coupling, I mean, they're independent operators. External coupling, there's some mixing problem. There's some kind of matrix associated with the dilatation operator. When you diagonalize, there's one component with dimension 1. What's the other one? What is the other component? The other combination. What dimension do they have? The higher dimension?
No. Both of them has dimension 1.
But you say a combination. Here, do you have a single operator of dimension 1 or two operators?
So
You said a combination.
Okay, the confusion part or the unclear part in this case is that
Oh, you don't see the degeneracy.
yeah.
You don't know the degeneracy. You just know one. You just know there has to be.
Yeah. From the general conformal block, we just know there is an operator that contributes with conformal dimension 1, but it's not clear whether it is this one or a combination of the two. That is not clear.
But from the explicit model, you must be able to answer that, especially with this field transformation, this field dependent transformation.
Yeah, with the field redefinition, I did some computation and it seems like it should be this one.
Because if that's the case, that's consistent with what you claimed before, like this phi doesn't develop anomalous dimension.
That's a good point. So my take was this one.
Okay.
Somehow I didn't manage to.
I mean, that's why I asked you this question, because they will mix and then generally they will develop an anomalous dimension, and then phi itself will not be protected. It should not be marginal anymore.
Yes. That's a good point.
Because if you look at your action, classically you have two marginal parameters.
Yeah.
Question is, quantum mechanically, do you have just one or less or two?
I think there's two.
If there are two, then you have two independent dimension 1 operators.
Yes, I think there are two independent dimension 1 operators.
That's a non-trivial claim because their OP has to satisfy properties such that they are independently normalized as you turn on the couplings.
Yeah, that's a good point. I haven't had a clear thought about this spot. But my belief was that there are two independent dimension 1 operators. Yeah. Good. And then the other P0 is just 1. So with this combination, we can compare the result from our model to the general analysis, and indeed they match. Maybe I can tell you about. I have 1 minute.
Yeah, minus 5 minutes.
Okay, I can also finish here. Yeah, this is basically what we have considered, and they are good with some future studies, like you can consider bulk fermion, or to consider some other interacting model. Or actually, there's one more interesting thought is that maybe it's also worth to consider finite temperature case. Might be more interesting. Yeah, that's all what I want to say. Thank you so much.
Any question for Dongsheng? Dongsheng will be here for a while, so if you have questions, come talk to him. Thank you, Dongsheng, again.